But I just have to start off with like reality check. Okay, we're just gonna have a moment with some numbers. So let's say that I had, I'm gonna make this really fairly extreme. Six plus 5, and I divided that by 6. Tempting, perhaps, to somehow cancel those 6s out. However, it would be really cool if I could. But let's take a moment to think about what this means numbers-wise. 6 plus 5 on the top, well, that's equal to 11. And then I'd have a 6 on the bottom. I don't know what 11/6 is as a fraction, but I do know that it's fairly close to 2. Because if that were 12/6, that would be 2-ish. So this is pretty close to 2. All day long, when it's not numbers and it's letters involved, I see students do this, cancel out those 6s, and somehow get a 5. It doesn't work with numbers. And if it doesn't work with numbers, it also doesn't work with letters. The moment that we put X's or A's or B's or Y's into a problem, those letters are just a placeholder, right? It's a placeholder for some number that I haven't told you yet. So if it doesn't work with numbers, it also doesn't work with letters. What would work here, if you really wanted to, was to take that 6 plus 5/6 and break that apart as a 6/6 plus a 5/6. These are equivalent. That's 1 plus 5/6. That's fine. What we can't do is cancel those 6s out. Now, to switch that around to be something with letters, that also means that if I had like X plus 3/X, that's it. That's what it equals. There isn't anything else we can do to this. If you really wanted to rewrite it in some way, we could look at that X on the bottom and say, this sort of came from getting a common denominator between two things that maybe look like X/X plus 3/X. That would be fine. But this, there just isn't a lot we can do with it. We're gonna leave it alone for the same reason that I can't cancel that 6 out when it's just numbers. Okay, good times, moving on. So when can we cancel things out from the top and the bottom? When everything's being multiplied together and something's being multiplied by 1. So just practice with numbers for a second. This part you can write down if you like. So to get some practice with messing with numbers, if I had 5 times 3 times 7 over 6 times 10, and what I was trying to do was to simplify this. And I know simplify is like the least, it really is the most terrible instruction that I could give. But in general, if we say simplify, it does mean to reduce to lowest terms. Well, since all of my things are numbers and they're all being multiplied together, one option that I have to reduce this to lowest terms is to think about breaking anything up into its smaller factors. 5, 3, and 7, they're all primes, so there's nothing more that I can do with those. But 6 and 10, I can rewrite each of those. That 6 I can rewrite as 3 times 2. And the 10 I can rewrite as 5 times 2. I'm going to do one extra step here that is not necessary, but I'm doing it anyway. I'm going to regroup things so that I have multiplication by 1. That 3 over 3, I'm going to group together. And I'm going to group the 5 over 5. And then I'm left with a 7 on the top and the 2 times a 2 on the bottom. Now that I have things that are multiplying and equal to 1, that 3 over 3 is a 1, that 5 over 5 is a 1, and my final answer here would look like 7 over 4. It would also be fine to leave this looking like 7 over 2 squared. Either one of these would be totally fine as a final answer. Well, all of that lovely practice factoring that you got in chapter 5, we're about to use that so that we can practice simplifying algebraic expressions that have letters and numbers. So let's start off with something like, I'm going to start off slow here. So how about 2 over 6t minus 2? Okay, our objective is to simplify or reduce to lowest terms. Tempting, but wrong to cancel the 2's out right now. I have to have everything written as multiplication so that I'm finding something that's multiplied by 1. So my first step is to hope that I can rewrite this with some factors. In that denominator, it looks like I have a greatest common factor between those two terms of 2. So I can pull a 2 out, and then I'm left with 3t minus 1. Now that I've got that 2 out as multiplication, this 2 over 2, that is a 1, and I'm looking at 1 over 3t minus 1. And that's my final answer. Can't go cancel those 1's out. I've got subtraction down there. The only reason that it works, that's why I don't even like the phrase canceling. I'm always looking to find a 1. I'm looking for that multiplication by 1. Okay, I'm going to give you all one. And how messy should I make it? Yeah, okay. So let's practice the factoring this morning. X squared minus 7x plus 12. 2x squared. Oops. Sorry, plus 24. Hold on. Let me make that a minus. So if we're trying to reduce this to lowest terms, or sometimes the instructions are just going to say simplify, that very first step is to hope that I can rewrite everything as multiplication. So we're hoping that things factor. So I'll give you a minute to try it on your own. you're still working at it, you're probably doing more work than you need to be doing. So if you're still working at it, you probably did more work than you had to. I was kind of mean, not really. You can absolutely factor the top and the bottom here, but if you are clever, you might notice that the bottom is exactly twice the top. So if I take that greatest common factor out of the bottom first, then I'd be left with x squared minus 7x plus 12, which happens to be exactly what, oops, that says 17, which happens to be exactly what was already on the top. It's okay if that entire thing can factor out. So this entire thing on top and this entire thing on the bottom, they're identical, which means when I divide by them, that whole thing is just going to leave me with a 1. And there's a question in the chat about, like, could you reduce the individual terms? So just for a second, let's see what would have happened if we had reduced the individual terms. So if I thought about looking at the x squared over 2x squared, if that's the only thing I had in the problem and there was no addition or subtraction, that would definitely reduce to be 1/2, because the x squared over x squared would cancel out. But I'm adding and subtracting stuff from that. So the only way that we get to cancel is if we have everything written as multiplication. That whole idea of canceling, I wish we had a different word for. Because what it really means is that you have found a multiplication by 1 somewhere in the problem. And since multiplying by 1 doesn't change what we have, that's the reason that we usually get rid of it. We get rid of it and we do that by canceling. Let's do another example. And hopefully after many examples, things will start to look a little better. Oh, I've got lots to choose from here. Well, let's do something like x squared minus 9 over x minus 3. So this is another one where I understand the temptation to take that x squared and x and simplify that and take the 9, the -9 and the -3 and simplify that. And occasionally you might accidentally end up with the right answer for the wrong reason. But what we actually need to do here is to factor. The top is one of our special factors because it's the difference of squares. So the top is going to factor as x minus 3 times x plus 3. And then the bottom is an x minus 3. So anytime I have a piece that's like together with addition or subtraction, I kind of have to treat that as a whole unit. So x minus 3 is its own thing. And it's the same as this x minus 3 on the bottom. If I regroup that, and sometimes it helps to actually write it as regrouping it so that you can very clearly see that you're multiplying by 1. But that x minus 3 over x minus 3, that's what's going to be equal to 1. And my final answer is going to be x plus 3. Now there's something subtle about these 3 problems that we just did. And that subtlety is going to be important in both pre-calculus and calculus. So I do want to point it out here. This expression is equivalent to this expression, but there is a value of t that we can't plug into the function. And sometimes we state that as a restriction on the variable. And the restriction on the variable here would be that I can't actually plug in 1/3 for t. If I tried to plug in 1/3 for t on this example, then in the original expression, I'd have 2 divided by 0. You're going to talk about how to deal with dividing by 0 in calculus, but dividing by 0, a number divided by 0 is not equal to 0. A number divided by 0 could be 17 or 42. Yeah, what, right? Like weird. Yeah. So let's talk for a second about what happens if we tried to divide by 0. So let me go back to like, if I had 6 divided by 3, y'all know that's equal to 2. And it's equal to 2 because 3 times 2 is equal to 6. Well, I claim that weird stuff happens when we divide by 0. So if I had 2 divided by 0 and I wasn't sure what that equaled to, I feel like I'm going to sneeze, but it's not here yet. If I were to write out that because statement looks like 0 times something is equal to 2. Is there any number that I can put in there that you can think of that is always going to give me 2? Because 0 times something is supposed to equal what? Well, if 0 times something is supposed to equal 0 and this is giving me a 2, then I'm going to say this is just something weird and you will explore it in calculus. But for the time being, this just doesn't make sense for us. So we restrict our variable to not plug in 0 to the denominator. Now in calculus, what we're going to do is get really, really close to 0. And when we get really, really close to 0, interesting things happen. But for now, we're just going to be practicing that if I have something that starts off as x squared minus 9 over x minus 3, and we have simplified that to be x plus 3, we're going to be careful to also include a restriction on the variable. And sometimes we write that as for x not equal to 3. Or we can say the restriction is that x is not 3. And that symbol of the equal with the line through it means it's not equal to. And from now on, anytime we're doing a problem where we have variables in the denominator, I'm going to start the problem by finding the restriction on the variable. So let's say that I've got x squared plus 2x plus 4 over x cubed minus 8. I'm going to start by saying, okay, we've got a denominator here. So my restriction is that that denominator cannot be equal to 0. Well, luckily I gave us something that factors. X cubed minus 8, that's one of our special factors. So that x cubed minus 8 is going to factor as x minus 2 times x squared plus 2x plus 4. And then on top we had x squared plus 2x plus 4. Okay, that's convenient. My top and my bottom match. So I know that these are going to cancel out. I know we don't have a better word for it in math. These two are a creative multiplication by 1. And I get 1 over x minus 2. But we have to say for x not equal to 2. Right? That was our original restriction on the variable. And for the problems in the homework, they will remind you explicitly to find the restriction on the variable if you haven't done any of the problems in this section yet. Okay. $9.23. Everybody ready to get some factoring going? Okay. So one of the cool things about the problems in chapter 6 is you often get like 4 factoring problems for the price of 1. So we're going to reduce to lowest terms. And here we go. Let's say I've got x squared minus 4 times x squared plus x minus 12, whole thing over x plus 4 times x squared minus 5x plus 6. Well, the first thing that I want to do is to figure out what the restriction is. And in terms of the restriction, I know that x plus 4 cannot be equal to 0, but also x squared minus 5x plus 6 cannot be equal to 0. Now we can turn both of those into like an actual list of numbers that x can't be equal to. Because if x plus 4 can't be 0, that means that none of my pens want to work today. That means that I can't have that color. That means that x cannot be equal to -4. Well, if x squared minus 5x plus 6, if that were going to equal to 0, and I needed to solve that, I sure hope it factors. I need 2 numbers that multiply to give me +6, but add to give me -5. So I'm looking at a -3 and a -2. And that can't be equal to 0, which means x can't be equal to 3 or 2. So I've got 3 numbers that x is not allowed to be equal to. And once I've got that restriction, then I can go ahead and reduce to lowest terms. Since we already got that second part down here factored, I'm going to go ahead and write it in its factored form and give you all a minute in case you haven't done it yet to get the top factored out and hope that something cancels. I think both pieces are like that. How's our factoring going? I'll do the easy one. X squared minus 4 factors as x minus 4 times x plus 4. Anyone want to give me the factors on this next piece, the x squared plus x minus 12? Positive 4, negative 3. I think that's going to work out. I'll have plus 4 or minus 3. That'll give me the plus x. A plus 4 times a minus 3 will give me the negative 12. Looks good to me. So now in all of that jumble, I'm looking for anything that works out to be 1. So x to the 4th over x to the 4th. That's a 1. X minus 3 over x minus 3. That's a 1. And now on the top, I still have the x minus 4 and an x plus 4. And on the bottom, I still have an x minus 2. So that's the best I can do. And we can include for x not equal to 3, 2, or negative 4. Notice that the restriction on the variable comes from our unsimplified form. So it is important to check for those restrictions before you start canceling stuff out. Now, trust me, no one's going to make you graph this anywhere. But if you were graphing it, what's happening when you have factors like that that cancel out is you actually have a hole on the graph. Because it's a place where when you try to plug in that x value, you actually don't get a y value back because you're dividing by 0. So good times. Okay. More fun? Yeah, so there's a request to like focus a little bit more on the restrictions piece. So for sure, let's do that. Yeah. So I'm actually going to give us one that's already factored just so that we can focus on the restrictions. So let's say that our instructions are to reduce the lowest terms. Or simplify. And let's say that I had something that was a little bit messy, but let's say I've got x plus 1 times x minus 2 times x minus 3 over x plus 4 times x minus 3. So as soon as I see this expression, I can automatically know what my restriction on the variable is because I can't divide by 0. So my restriction is going to be whatever makes the denominator equal to 0. So thinking about that restriction, I'm saying that x plus 4 times x minus 3 cannot be equal to 0, which means x plus 4 can't be equal to 0 and x minus 3 can't be equal to 0. So x cannot be negative 4 and x cannot be positive 3. That's just like my list of restrictions. Now I can move on and reduce this thing to lowest terms. Well, since I already got it factored for us, we're kind of ready to go. My x minus 3 over x minus 3 is equal to 1. So this, in its most reduced form, I would write as x plus 1 times x minus 2 over x plus 4. And then I would just state for x not equal to -4 or +3. Like, will you have to state the restrictions on the, yes, you will have to state the restrictions on the variable. Yeah. By the way, like, one of the reasons that I don't like the word simplify is there are times when it's great for this to be in a factored form. And there are also times when it would be really nice for the top to actually be multiplied back out to look like x squared minus x minus 2 over x plus 4. These are equivalent. Personally, I don't actually care which form you put if I ask you to reduce to lowest terms. Technically, these are both reduced to lowest terms. My general suggestion is don't do extra work unless you need to, right? So if there was something about the problem where this was going to be helpful later, then sure, you could multiply the top back out. But if you've already done the work of factoring it, don't like undo the work you already did. Just leave it factored. Once upon a time, back at the beginning of the quarter, I think we talked about this a little bit with numbers, but let's revisit it. So if I had 3/4 times 2/5, because everything's being multiplied together here, I can think about that as one big fraction with a 3 times 2 on the top and a 4 times 5 on the bottom. And then I can break apart that 4 and say that 4 was actually, oops, the 4 was actually 2 times 2. And then do my magic 1 thing and end up with 3/10. But when I'm actually dividing something instead of multiplying, let's make this 1/7. And I've written it this way, although we basically never write it this way in calculus. We almost never use this division symbol. I know we talked about that the first week, but it does show up sometimes, so we got to be able to deal with it. This is equivalent to saying that I had 3/4 whole thing divided by 1/7. And that is equivalent to 3/4 times 7/1. And we can revisit why that works, but I'm thinking at this point, we're just going to use it that dividing by a fraction is the same as multiplying by its reciprocal. Once this is in multiplication form, then I can multiply straight across and say that's 21/4. Well, if it works for numbers, it's going to work for letters too. So let's do an example with division. And let's say that I've got 6x minus 30 or x squared minus 8x plus 15 divided by, and I'm writing this the way that it is most often written in our textbook, even though that is rarely how it gets written, how it would appear in calculus. this would generally look like this garbage, giant division bar divided by that garbage. But I'm still going to start off the same way and say, hey, I've got two fractions happening here. I need to be concerned about anywhere that I might be dividing by 0. I just realized they gave us kind of a terrible problem in terms of stating the restrictions. We'll talk about the restrictions in a second. Why don't you all get everything factored? And then we'll mess around with it and talk about the restrictions on the variable. I know it's 4 factoring questions for the price of 1. Should I do the fast factoring for us? It's also possible not everything factors. We'll find a practice from the book, but that doesn't mean that they all factor. That's what they I guess there aren't a lot of choices for the x squared minus 8x plus 15. Don't have a lot of choices for how to multiply to get 15. So I think I'm looking at -5, -3. Doesn't matter how you factor this last one. I tend to use the x method if the coefficient on my x squared is not 1. But we can also go straight into thinking about this with factors. I don't know if anyone has a preference of which way I do it. Cool. I know for sure that to get a 2x squared, I need a 2x and an x. And now if I think about factors of 9, it's either 9 and 1 or 3 and 3. And I don't think 9 and 1 is going to work. Either way that I put the 9 and the 1, I don't think I'm going to get a 9 in the middle. I think that's got to be a 3 and a 3. And I think they need to both be negative. so that I've got a negative 6x and a negative 3x adding up to give me that negative 9 in the middle. Okay. It said that after we got it all factored, then we could talk about restrictions on the variable. This one's going to be complicated, and I apologize. Well, from the original problem, we've got these two fractions. So I can already list off that I know x can't be equal to 5 or 3 or 2. By the way, that 8, that doesn't say like x minus 8 or x plus 8. It just says 8. 8 is never equal to 0. So we don't have to worry about that part at all. But there's an extra piece that we have to worry about on the restriction. Because dividing by this fraction is equivalent to multiplying by its reciprocal. So when I do that and I flip it over, oops, I also have to concern myself with the new denominator that we're going to get when we flip it over. I promise not to ask you anything this gross on a quiz. Or if I did, I would not ask you to state the restriction on the domain. I mean, the restriction on the variable. But technically, we should also add to our list of restrictions now anything that's in the denominator after we rewrite this. We've already got 3 taken care of. It's already in our list of restrictions, but our new addition to our restriction list is going to be 3 halves from this piece right here. Now I'm ready to go through and find anything that's equivalent to 1 because everything's being multiplied together. I can switch the order that everything is in there if I need to. It looks like the x minus 5 over x minus 5 is the only thing that's going to cancel out for us. Annoying, but true. So to write my final answer, I would write this. I would take a moment to multiply the 6 times 8. So I would have 48x minus 2. And the most like compact way to write what's on the denominator is to have that 2x minus 3 and then times x minus 3 whole thing squared. And that's the most compact way that I could write that final answer. Sometimes we do a whole lot of work and nothing cancels. Yeah, so the question on why the 3 halves for the restriction, I know it's super subtle. But when we take this fraction and write it in its equivalent multiplied by the reciprocal form, now I need to take into account the fact that 2x minus 3 can't be equal to 0, which means 2x cannot be equal to 3, which means x can't be 3 halves. We already had the x cannot be equal to 3, so we don't have to like put it in the list twice. Dun, dun, dun. Okay, we have 4 minutes left. So let's talk about some word problem vocabulary that comes up in chapter 6. And there are a couple of different ways that this gets phrased, like in different calculus textbooks. So I want to make sure that we've seen both. If I say x varies directly with y, then that phrase varies directly means the same thing as saying X is proportional to and both of these mean that if I were writing this as an equation, X is equal to a constant times Y. Now I've chosen a constant of A. The truth is that the more common constant is to write the letter K. But you can, in fact, write any letter you want. If I say X varies in, well, and so let's see what that looks like in the context of a problem. So if I said X varies directly with Y, X is 10 when Y is 6. What is Y when X is 4? So I'm going to start by taking that very first statement that X varies directly with Y. And as soon as I see that, I'm writing X is equal to a constant times Y. Now I'm thinking about what's the value of that constant so that I can answer the question. And to figure out the value of that constant, I'm hoping that we've been given a point. We've been given a value of X and Y like at the same instant. So X is 10 when Y is 6. So if I plug in 10 for X and 6 for Y, I said 6, I wrote Y, and 6 for Y, then that corresponds to what that second sentence says, which means my value of A is 10 over 6. I could say that's the ratio, or that's the constant of proportionality. By the way, we could reduce that because 10 and 6 can both be written as something times 2. So I could say that that's equivalent to 5/3. Once I know that value, now I can answer the final question. What is Y when X is equal to 4? Well, plugging that into our formula, I'm going to have 4 is equal to 5/3 of Y, which means Y is equal to 4 divided by 5/3, or if you like, Y is equal to 4 times 3/5. So I'm going to get 12/5 is equal to Y. If you are working through the homework in chapter 6, there are 2 problems about like boats going upstream or something. Don't do those. I think they're problems 14 and 15. I mean, you're welcome to if you really want to. Don't do them. I've got office hours this morning in person over in C class from 10:30 to 11:30, and I've got office hours on Zoom this afternoon from 2 to 3. Happy to work through stuff with anyone, but I am out of time now.